Sometime around 2 in the morning, on any given night in New York City, something extraordinary is happening. Not above ground, where the last bars are closing, and the garbage trucks are beginning their routes, and the yellow cabs are ferrying the last stragglers home through the wet amber light. Not on the subway platforms, where the overnight trains roll through on slightly extended schedules, carrying nurses and hotel workers, and the occasional insomniac who just needed to go somewhere. Not in the all-night diners, where someone is always getting coffee at an hour that doesn't make any practical sense. Below all of that, below the subway tunnels, below the electrical conduits, below the fiber optic cables, and the steam pipes and the water mains, and the layers of compressed history that make up the geological record of 4 centuries of human settlement. Below all of that, something is moving. It has always been moving. It moved last night, and it will move tomorrow night. And it has been moving, in one form or another, since before anyone alive today was born. It is one of the most sophisticated systems of engineering that any city on Earth has ever built. And on any given day, the overwhelming majority of the 8.5 million people who live directly above it and directly depend on it for their continued health and survival give it absolutely no thought whatsoever. That's actually by design. The whole point is that you don't notice it. The whole point is that it works so quietly, so consistently, so completely beneath your awareness that you can go your entire life in New York City without once genuinely thinking about what happens after you flush your toilet. So let's think about it now, because the story of what happens after you flush in New York City is, it turns out, one of the genuinely great stories of human engineering and human ambition and human stubbornness. It's a story that spans more than a century and a half. It involves cholera and political corruption and the Hudson River and a neighborhood in Brooklyn that most people have never heard of and a collection of underground tunnels large enough that you could ride a bicycle through them if you were sufficiently motivated and had the right permissions, which you almost certainly do not. It involves people who go to work every day in places that would make most of us deeply uncomfortable. It involves chemistry and biology and physics and politics and money, always money. And it involves an ongoing, never-finished negotiation between a very old city and a very complicated problem that the city's founders created more or less by accident, and that every generation since has been trying, with varying degrees of success, to solve. The story also involves the harbor. Beautiful, complicated, historically significant New York Harbor, which was once so polluted that it was, by certain measures, functionally dead, and which is today, by most reasonable assessments, cleaner than it has been in 100 years. That didn't happen by accident either. But we're getting ahead of ourselves. Let's start at the beginning. Let's start, in fact, before the beginning. Let's start with what New York looked like before any of this existed, because understanding what the city was before the infrastructure can tell you an enormous amount about why the infrastructure ended up being built the way it was, and why some of the choices that were made in the 19th century are still shaping the choices that engineers are wrestling with today. Chapter 1. The River Beneath the River. Origins of New York's Water System. There is a river in New York City that you will never see. You can't see it because it no longer exists on the surface. It was paved over and built over and essentially erased from the visible landscape sometime in the middle of the 19th century, which sounds recent until you realize that it was already ancient when the Dutch arrived in the early 17th century. The Lenape people who lived on the island of Mannahatta, as they called it, knew this river well. They called it by names that have not entirely survived the colonial period, but the geography it carved into the land has absolutely survived, hidden in plain sight in the way that Manhattan's street grid suddenly tilts and shifts in certain neighborhoods, following the contours of a waterway that the streets were laid over as the city grew. This was the Collect Pond, and it fed a stream that ran roughly where Canal Street runs today, which is, you might notice, not an accident of naming. The stream drained the pond southward toward the Hudson. The Collect itself sat in what is now roughly the neighborhood of Foley Square, near the courthouse district in Lower Manhattan, and for the first 2 centuries of European settlement in New York, it was an important source of fresh water for the growing city. You can see where this is going. By the middle of the 18th century, New York had grown to perhaps 15 or 20,000 people, and the Collect Pond had begun to receive a level of attention that no body of water should ever receive. Slaughterhouses operated on its banks. Tanneries dumped their chemical waste into it. Breweries found it convenient. The general runoff of an increasingly dense urban settlement found its way there through the simple mechanism of gravity, which does not distinguish between rain and everything else. By around 1800, the Collect Pond was, by any reasonable description, a disaster. Visitors to the city described it as an open cesspool. The water was dark and foul-smelling, and no longer fit for any human use. The city eventually had it drained and filled in, which was accomplished through considerable effort between approximately 1803 and 1811. But filling in a pond does not actually solve the underlying problem of what the ground beneath the fill is made of. The neighborhood that was built over the filled pond, 5 Points, which would become one of the most notorious slums in American history, sat on ground that was perpetually damp and unstable, because you cannot simply erase a body of water by covering it with soil. The water goes somewhere. It always goes somewhere. This is, in miniature, the fundamental lesson of urban water management. Water goes where it wants to go. You can redirect it. You can channel it. You can pump it and filter it and treat it and move it across hundreds of miles of pipes and tunnels and aqueducts. But you cannot make it stop being water. And you cannot make it stop following the rules of gravity and physics that have governed it since before the first human being looked at a stream and thought about building a city nearby. New York has been learning this lesson over and over again for 400 years. In the early colonial period, the settlement on the southern tip of Manhattan was small enough that individual wells provided adequate fresh water for most residents. This works fine when you have a few hundred people living on an island surrounded by water. It works progressively less well as the population grows, because the island of Manhattan is not as large as the ambitions of the people who have settled on it, and because the geology of Lower Manhattan, essentially a layer of relatively permeable soil and fill sitting on bedrock, means that wells tend to be vulnerable to contamination from the surface in ways that are not always visible until significant damage has been done. By the time of the American Revolution, the water supply situation in New York City was already a matter of some concern. The city was growing rapidly. The wells were increasingly suspect. Various private companies were formed over the following decades to try to address the problem through the creation of a piped water system, the most notable of which was the Manhattan Company, founded in 1799. The Manhattan Company is interesting primarily because it was founded by Aaron Burr, who used the company's charter, which technically gave it the right to use surplus capital for any purpose whatsoever, to also charter a bank, which is what he actually wanted to do all along. The Bank of the Manhattan Company eventually became Chase Manhattan Bank, which eventually became J.P. Morgan Chase, which is today one of the largest financial institutions in the world. The water system Aaron Burr created was, by contrast, almost immediately inadequate and not particularly well maintained, and it remained the primary water supply for New York City through the great yellow fever epidemics of the early 19th century, which were not helped by the quality of the water people were drinking. The truly transformative moment in New York's water history came in 1842 with the opening of the Croton Aqueduct. This was an engineering achievement of genuine historical significance. One of those moments when a city decides to take a problem seriously and spends the money and the effort to actually solve it, rather than to manage it indefinitely. The Croton River in Westchester County, about 40 miles north of Manhattan, was dammed to create a reservoir and a gravity-fed aqueduct, built in the style of the ancient Roman aqueducts. A brick-lined tunnel approximately 8.5 feet tall and 7.5 feet wide was constructed to carry the water from the dam all the way to distribution reservoirs in the city. The old receiving reservoir sat where the great lawn in Central Park is today. The distributing reservoir, a massive Egyptian revival structure that was one of the great architectural statements of the period, sat on 5th Avenue and 42nd Street, where the main branch of the New York Public Library now stands. The arrival of Croton water in New York City on October 14, 1842, was celebrated with something close to hysteria. Guns were fired, bells rang, fountains ran in the streets. People had not been drinking clean, reliable water for so long that the arrival of it felt miraculous. A journalist at the time wrote that the water tasted like rain, which sounds like faint praise, but was in fact the highest compliment he could offer, given what New Yorkers had been accustomed to drinking. But here is where the story takes its inevitable turn toward complication. Clean water coming in is only half of the problem. The other half is water going out. And by the time New York got serious about the supply side in the 1830s and 1840s, the disposal side had been growing into a crisis for decades. The question of where human waste went in 19th century New York is not a delicate subject, but it requires a certain fortitude to examine honestly. The short answer is, mostly into the ground, or into the street, or into the nearest body of water, or some combination of all three. Most households in New York, before the construction of the sewer system, used privies, outhouses, essentially, located in the back of their properties. The waste accumulated in brick-lined pits beneath these structures, which were supposed to be periodically emptied by a class of workers known colloquially as night soil men, who came in the darkness to cart the material away. Where they took it is its own story. Initially, to farms in the surrounding region, where it was used as fertilizer, but increasingly to anywhere convenient as the city grew and the farms became more distant and the economics of the operation became less viable. As the city grew denser, the privy system became inadequate in ways that were not subtle. The pits overflowed. The ground became saturated. In the tightly packed tenements of Lower Manhattan, where dozens of families might share a single backyard with a single privy, the situation during the warm summer months was, by all accounts, extraordinary in the worst possible way. And then New York got indoor plumbing. The arrival of Croton water and the laying of water mains through the streets of the city in the years following 1842 created a sudden and powerful demand for indoor plumbing. Flush toilets, which had been a theoretical luxury before, became practical appliances. Hotels and wealthy residences installed them quickly. By the 1850s, flush toilets were spreading throughout the city's middle-class housing stock. Within a generation, they had become effectively universal in new construction. This was wonderful, genuinely wonderful, for the people who now had access to indoor plumbing and flush toilets. It was catastrophically inconvenient for the city's sanitation infrastructure, because the city's sanitation infrastructure essentially did not exist. Where did the water go when you flushed? Into the cesspool beneath the house, which was already struggling to handle what the privy had been putting into it, and which was absolutely not designed for the sudden addition of flush water from a household connection to the city water main. The cesspools overflowed. They flooded basements. They soaked into the ground. The ground, particularly in lower Manhattan, where the water table was high and the geology unforgiving, became saturated with something that was not water, in any sense that you would want to use the word. The city had, essentially, created an indoor plumbing system without first creating a place for the indoor plumbing to drain. This situation could not continue indefinitely, and it did not. What came next would define New York's physical infrastructure for the next century and a half, and its consequences, intended and unintended, are still playing out today, below your feet, right now, at this very moment. Chapter 2. The Great Stink and the Men Who Solved It. Every city that has grown quickly has gone through a version of what New York went through in the second half of the 19th century. London went through it first and most dramatically, with a summer in 1858 that has passed into historical legend as the Great Stink, a period when the smell coming off the Thames, loaded with the untreated sewage of 3 million people, became so overwhelming that Parliament, which sits on the banks of the river, was forced to hang sacks soaked in chloride of lime over its windows in an attempt to make the smell bearable enough for legislators to continue working. It didn't entirely work, but it did produce something that the smell alone had not produced in decades of discussion and committee reports. A political consensus that something had to be done. London's response to the Great Stink was Joseph Bazalgette, a civil engineer of exceptional talent and organizational ability, who designed and oversaw the construction of a sewer system for London that, when it was completed in the late 1860s, was the largest public works project in the world. Bazalgette's sewers still serve London today. Parts of them are still carrying waste in the original Victorian brickwork, which is either a tribute to the quality of Victorian engineering or a reflection of the difficulty of digging up an entire city's worth of underground infrastructure, or possibly both. New York's version of this story is less dramatic in its particulars, but no less consequential in its outcomes. New York did not have a single Great Stink. What it had instead was a relentless, grinding accumulation of disease, discomfort, and municipal dysfunction that eventually produced the political will for the same kind of comprehensive solution that London had reached through more theatrical means. The disease question is the one that ultimately drove everything. Cholera is transmitted through contaminated water. This was not, in 1850, a universally accepted scientific fact. The germ theory of disease was still being established, and the idea that invisible organisms in water could kill people was still fighting against the older miasmatic theory, which held that disease was spread through bad air rather than contaminated water or food. But the epidemiological evidence was accumulating in ways that were hard to ignore. Cholera outbreaks in New York. There were major ones in 1832, 1849, and 1866. Consistently followed patterns that made more sense in terms of water supply than in terms of air quality. The neighborhoods with the worst water had the highest death rates. The people with access to clean water fared better. The causal mechanism was not yet fully understood, but the correlation was visible enough to motivate action. New York City began constructing a sewer system in the 1850s, initially in a somewhat piecemeal fashion. The early sewers were designed primarily to carry stormwater away from the streets, which were prone to flooding during heavy rain in ways that made them essentially impassable. The question of whether these storm sewers should also carry household waste, what engineers called sewage, was a matter of active debate. Some engineers and health officials argued strongly that sewers should carry only rainwater, and that household waste should continue to be dealt with through privies and cesspools, for the simple reason that if you combined the two streams, you ended up sending raw sewage directly into the rivers and the harbor, which seemed obviously bad. Others argued, with equal force, that the only practical solution to the cesspool problem was to connect household drains to the sewer system, because the alternative, maintaining and emptying cesspools for a growing urban population, was simply not sustainable at scale. The cesspools were already failing. The ground was already contaminated. Putting the waste directly into the rivers, while not ideal, was at least moving it away from where people lived and drank and breathed. This argument, which was essentially an argument between bad and worse rather than between bad and good, was resolved in favor of the combined system, sewers that carried both stormwater and household waste, for reasons that were partly practical and partly a reflection of the engineering consensus of the period. The combined sewer system became the standard model for American cities in the second half of the 19th century, and New York built one of the most extensive ones in the world. It is worth pausing here to note that this decision, made by engineers and politicians in the 1850s and 1860s, for reasons that seemed entirely reasonable at the time, is the source of one of the most persistent and expensive engineering headaches that New York City faces today. We'll come back to that in some detail later. For now, just hold the thought. When it rains in New York City, the rain goes into the same pipes as everything else. The man most closely associated with the actual design and construction of New York's sewer system in this period was Julius Adams, a civil engineer who produced a comprehensive plan for Brooklyn's sewers in 1857, and Egbert Viel, who served as engineer-in-chief of Central Park, and produced important maps of Manhattan's underlying topography that remain useful to engineers today. Viel's topographic map of Manhattan, which showed the original watercourses and wetlands buried beneath the city's streets, was so accurate and so comprehensive that it was used by engineers for decades and is still consulted today when construction projects in Lower Manhattan encounter unexpected water seepage, which they do with a regularity that suggests the buried streams of Mannahatta are patient about these things. The construction of the sewer system in New York during the second half of the 19th century was an enormous undertaking, accomplished largely by Irish and later Italian immigrant labor, working in conditions that were significantly more dangerous than anything that would be permitted today. The men who dug the sewers worked in cramped tunnels with hand tools, in air that was frequently unpleasant and occasionally toxic, for wages that would strike us as appallingly small. They were building something that would outlast them by generations, something that their descendants would depend on without knowing their names or thinking about their work. This is one of the persistent ironies of infrastructure. The people who build it are almost always forgotten in proportion to how essential what they built becomes. By the 1880s, New York had an extensive sewer network, but it had something that was not quite a sewer system in the modern sense, because the sewers went to the rivers and the harbor, and that was that. There was no treatment. There was no processing. The waste moved from the houses to the pipes to the water around the island, and there it stayed. For a while, this seemed to work. The harbor is large, the tides are powerful, and for a city of 1 million people, the dilution factor was sufficient that the worst effects were localized near the outfall pipes and were not visible across the broader harbor. But New York was not going to stay a city of 1 million people. By 1900, New York had grown to more than 3 million people, following the consolidation of the 5 boroughs in 1898. By 1910, it was approaching 5 million. By 1930, it was nearly 7 million. Each of those additional millions of people was connected to the sewer system, and each of them was contributing, every day, to a load on the harbor that was growing far faster than the harbor's natural capacity to absorb it. The harbor was beginning to die, and the people who cared about such things were beginning to say so loudly enough that someone eventually had to listen. Chapter 3, The Journey Begins, From Toilet to Tunnel. Let's talk about what actually happens, not in the abstract, not in the historical, in the specific and present tense. You flush a toilet in New York City, right now, this moment. Let's say it's an apartment in Brooklyn, somewhere in the middle of the borough, a 6-story building that was probably built in the 1920s and has been retrofitted with modern plumbing at some point since then. The toilet takes about 1.5 gallons of water per flush. Modern low-flow toilets use around 1.28 gallons, which seems like a small number until you multiply it by 8.5 million people and several times daily. The water and whatever it carries exits through the bottom of the toilet bowl and enters a small diameter drain pipe, typically 4 inches in diameter, that runs through the floor and connects to a slightly larger pipe running through the walls of the building. This vertical pipe, called the soil stack, runs from top to bottom of the building, collecting waste from every bathroom on every floor and exits through the basement into the building's main drain, which runs under the basement floor and out through the foundation wall. Here the first interesting physics begins. The building drain runs at a slight downward angle. The standard for residential construction in New York is a 1/4 inch of drop for every foot of horizontal run. And it carries the waste under the sidewalk and into the street, where it connects to the city's sewer system. At this connection point, there is a trap, a U-shaped section of pipe that holds a small amount of water that acts as a seal, preventing the gases that build up in the sewer system from flowing back into the building. These gases are a mixture of things, primarily methane and hydrogen sulfide. And while the methane is more dangerous in terms of explosive potential, the hydrogen sulfide is the one responsible for the characteristic smell that you encounter near sewer openings. A smell that the industry describes diplomatically as hydrogen sulfide odor, and that everyone else describes less diplomatically. The sewer pipe beneath the street in a residential Brooklyn neighborhood is probably 10 or 12 inches in diameter, made of concrete or sometimes of the older clay pipe that was standard in the 19th and early 20th centuries. It runs at a slight grade. Again, gravity is doing most of the work, and it collects waste from every building it passes, growing in diameter as it accepts more connections. By the time it reaches one of the larger collector sewers beneath a major street, It might be 18 or 24 inches in diameter. By the time it reaches one of the borough's major trunk sewers, it might be 48 or 60 inches, 4 or 5 feet across. The trunk sewers in Brooklyn run generally northward and westward, following the topography of the borough toward the harbor. Brooklyn is not flat. It has a ridge running through its center, the old terminal moraine left by the glaciers, and the sewer system was designed to take advantage of the natural slope of the land. Engineers in the 19th century understood that gravity was their friend, and they designed the system to work with it wherever possible. This was both economical and practical. A sewer that runs downhill by gravity requires no pumping, no electricity, no mechanical intervention. It simply flows. But Brooklyn is also not uniformly sloped, and there are areas of the borough where the natural grade does not cooperate with the need to move waste toward the treatment plants. In these areas, pump stations fill the gap. New York City has approximately 90 sewage pump stations distributed across the 5 boroughs, and they are perhaps the least glamorous pieces of critical infrastructure in the city. They are typically unremarkable buildings, often resembling small electrical substations or utility structures, sitting behind chain-link fences in industrial areas or tucked beneath elevated highways. Inside, large pumps, often several of them arranged for redundancy, lift the sewage from a lower elevation to a higher one, where gravity can take over again. The pump stations run 24 hours a day, 365 days a year. They are staffed by operators who monitor them and maintain them, and they are equipped with backup systems for the backup systems, because the consequences of a pump station failure are immediate and concrete in ways that most infrastructure failures are not. A pump station that stops working is a pump station whose collection basin fills up, and then the waste has nowhere to go, and then it finds somewhere to go on its own, which is invariably somewhere you don't want it to go. There is a saying among wastewater engineers that wastewater never stops. It doesn't matter what else is happening: storm, power outage, equipment failure, labor action. The water keeps coming. 8.5 million people don't stop using their toilets because the pump station is having a bad day. So the waste moves by gravity and by pump from the individual buildings through the local sewers to the trunk sewers to the larger interceptor sewers, which are the highway system of New York's wastewater network. The interceptors are where the scale of the whole enterprise becomes genuinely difficult to hold in your mind. Chapter 4. The Interceptor System. New York's Hidden Highways. There is a tunnel beneath the west side of Manhattan that runs roughly parallel to the Hudson River, deep enough below street level that you could fit a 2-story house in the space between the tunnel's ceiling and the street above. It is not a subway tunnel. It is not a utility corridor. It is a sewer, specifically one of the city's major interceptor sewers, and it carries, on an average day, a quantity of wastewater that most people would find surprising if they stopped to think about it, which most people do not. The interceptor system is the part of New York's wastewater infrastructure that was built, mostly in the late 19th and early 20th centuries, specifically to address the problem that had been building since the sewer system was first constructed. The sewers went to the rivers, and the rivers were dying. The interceptors were designed to intercept the flow before it reached the rivers and redirect it, first to collecting tanks, and eventually to the treatment plants that were built beginning in the 1930s. The concept of interceptor sewers was not unique to New York. It was, in fact, the same solution that Bazalgette had applied to London in the 1860s. Rather than letting the existing sewers discharge directly into the water, you build a larger sewer that runs along the waterfront, perpendicular to the existing sewers, and intercepts their flow before it reaches the river. The existing sewers still discharge, but now they discharge into the interceptor rather than into the water. The interceptor carries the combined flow downstream to a point where treatment or controlled discharge is possible. New York's interceptor system was built over a period of several decades, beginning in earnest in the 1890s and continuing through the mid-20th century. It involved digging very large tunnels through some of the most geologically complex and densely built urban terrain on Earth, and it remains one of the great, underappreciated engineering achievements of the city. The Manhattan portion of the system includes interceptor sewers running along both the east side and the west side of the island, collecting from the cross-street sewers and carrying the combined flow to pumping stations that lift it to the treatment plants. The West Side Interceptor, which serves the western half of Manhattan, terminates at the North River Wastewater Treatment Plant at 137th Street, which sits on a platform extended over the Hudson River, a plant whose story is itself remarkable, and to which we'll return. The East Side flows move to the Ward's Island plant, which occupies most of a small island in the East River between Manhattan and Queens. Brooklyn's interceptors run along the shores of Upper New York Bay and the East River, collecting from the borough's extensive sewer network and feeding the Newtown Creek and Red Hook treatment plants. Queens is served by a system that feeds the Bowery Bay and Jamaica plants. The Bronx has its own network feeding the Hunts Point and Tallman Island plants. And Staten Island, separated from the rest of the city by the harbor, has its own largely independent system feeding plants on the island itself. The full interceptor network spans, collectively, hundreds of miles of large-diameter pipe and tunnel running beneath the streets and shorelines of all 5 boroughs. Much of it is brick-lined tunnel of the same general construction as the Victorian sewers of London, and some of it is, in fact, roughly the same age. New York has sewer infrastructure that is well over 100 years old, still in service, still carrying waste through brickwork laid by hand in the 19th century. That is either impressive or alarming, depending on your perspective, and most wastewater engineers would tell you it's both. The interceptors were not built all at once, and they were not built according to a single comprehensive plan. They were built incrementally by different engineering teams working at different times with different budget constraints and different political priorities. And the result is a system that is not always as coherent as it might be if you were designing it from scratch today. There are places where the capacity of the interceptors is not well matched to the capacity of the local sewers they serve. There are places where the age and condition of the infrastructure are matters of genuine concern. There are places where the choices made by engineers in 1900 or 1920 are creating problems that their modern successors are still trying to resolve. This is, again, one of the universal truths of urban infrastructure. Nobody builds a sewer system all at once, and nobody builds it for the city that will exist a century later. You build it for the city you have, with the money you have, using the technology you have, and you hope that your successors will be able to adapt it to circumstances you cannot foresee. Sometimes they can, and sometimes they struggle with the inheritance you've left them. What goes through these tunnels is a substance that engineers call influent, what the public calls wastewater or sewage, and it is worth being precise about what that actually means at this scale. On a dry day, New York's combined sewer system carries approximately 1.1 to 1.3 billion gallons of wastewater to its treatment plants. That's a normal day, with no significant rain. The influent is primarily water, about 99.9% water by volume actually, and about 0.1% everything else. That 0.1% is human waste, food scraps from kitchen drains, soap and detergent, industrial discharges that have been pre-treated to remove the most dangerous components, pharmaceuticals that pass through human bodies and into the water supply, microplastics from synthetic fabrics, a remarkable variety of organic compounds from 1,000 different sources, and whatever else finds its way into drains in a city of 8.5 million people. 0.1% sounds small, but 0.1% of 1.2 billion gallons is 1.2 million gallons of material that is not water. And what to do with that material is the central challenge of the entire wastewater treatment enterprise. The interceptors bring all of it, all the water and all the not water, to the treatment plants. And the treatment plants are where the genuinely remarkable work happens. Chapter 5. The 14 Plants. Wastewater treatment across the 5 boroughs. New York City operates 14 wastewater treatment plants, 14 separate facilities, distributed across the 5 boroughs, each one a small city unto itself, running 24 hours a day, every day of the year, processing the collected wastewater of the surrounding neighborhoods and returning something much closer to clean water to the rivers and the harbor. The plants range in size from relatively modest operations that process tens of millions of gallons per day to the massive facilities at Newtown Creek and Ward's Island, which together handle the majority of the city's wastewater and rank among the largest wastewater treatment facilities in the United States. But all of them, regardless of size, work on the same fundamental principles that have not changed dramatically since the first treatment plants were built in the 1930s, even though the equipment and the chemical processes have been refined and improved enormously in the decades since. The first thing to understand about wastewater treatment is that it is, at its most fundamental level, an acceleration of natural processes. Left to itself, in a sufficiently large and healthy aquatic ecosystem, wastewater would eventually be processed and broken down by the biological and chemical activity that characterizes any living body of water. What wastewater treatment plants do is take those same processes, biological oxidation, sedimentation, filtration, and compress them from the months or years they would take in nature to the hours they take in a controlled facility. The second thing to understand is that the process is sequential. Wastewater treatment is not a single step. It is a series of steps, each of which removes something different from the water, and each of which depends on the previous step having been completed. The engineers who designed the early treatment plants in the 1930s understood this as a series of stages: primary, secondary, sometimes tertiary, and that framework is still the one that organizes modern wastewater treatment, even though what happens at each stage is considerably more sophisticated than it was 80 years ago. Let's follow the water in. The wastewater arrives at a treatment plant through the interceptor sewer, typically entering the facility through an underground channel or pipe that connects to what is called the headworks, the front end of the treatment process. At the headworks, the first thing that happens is screening. Screening means exactly what it sounds like. The wastewater passes through a series of bar screens, metal grates with gaps of varying sizes that physically remove the large solid objects that people have put into the sewer system. And people, it must be said, put a remarkable variety of things into the sewer system that do not belong there. The screens at a typical New York City treatment plant catch everything from rags and clothing to toys to what the industry, with notable delicacy, calls flushable wipes, which turn out to be not very flushable at all and which have become one of the more persistent headaches in modern wastewater management. They catch food waste and grease and occasionally items so surprising that the plant workers have developed a certain philosophical acceptance of human behavior that most therapists would envy. The material removed by the screens, called screenings, is collected and sent to landfill. It is one of the less glamorous waste streams in a system that is composed entirely of waste streams. And workers who deal with it develop a professional relationship with it that is distinct from any response a civilian might have. After screening, the wastewater enters the grit chambers. Grit is a technical term for the sand, gravel, and other dense inorganic material that washes into the combined sewer system during rain events. Material that would settle out and accumulate in the bottom of tanks and pipes if it were not removed early in the process. The grit chambers are long, relatively shallow channels through which the wastewater flows slowly enough that the heavier particles settle out by gravity, while the lighter organic material remains in suspension. The settled grit is collected, washed to remove organic matter, and disposed of, usually in landfill. With the large solids and the grit removed, the wastewater enters primary treatment. Primary treatment is fundamentally a settling process. The water flows into very large, circular, or rectangular tanks, primary clarifiers, and is held there for several hours, moving slowly enough that the suspended organic solids gradually sink to the bottom. The material that settles, called primary sludge, is continuously removed from the bottom of the tanks by slowly rotating mechanical scrapers. Grease and lighter material that float to the surface are skimmed off the top. What remains in the middle, the effluent from primary treatment, is considerably cleaner than what came in. It has lost perhaps 50 to 60% of its suspended solids and 30 to 40% of its biochemical oxygen demand, which is the technical measure of the organic load on the water. But it is not clean, not by any standard you would apply to water you wanted to return to a river. Secondary treatment is where the biological work happens, and it is where the modern treatment plant really earns its reputation. The secondary treatment process in most of New York's plants is based on a technology called activated sludge, which was developed in England in 1913 and represents one of the underappreciated scientific breakthroughs of the 20th century. The idea behind activated sludge is elegantly simple. You take the effluent from primary treatment, which still contains a significant organic load in dissolved and colloidal form, and you expose it to a dense population of microorganisms, primarily bacteria, under conditions that encourage those microorganisms to consume the organic material as rapidly as possible. The conditions that encourage this are a supply of oxygen, thorough mixing, and time. The oxygen is provided by aerators, large mechanical devices that either bubble compressed air through the water or use rotating paddles to churn the surface and incorporate air. The mixing ensures that the wastewater comes into contact with the microbial population throughout the tank. And time, typically 6 to 8 hours in a modern activated sludge plant, allows the bacteria to consume the organic material and reproduce. The result is a secondary effluent that has had 60 to 90% of its biochemical oxygen demand removed, and a dense biological mass, the activated sludge, also called mixed liquor in the jargon of the field, which sounds considerably more pleasant than what it actually is. That is separated from the effluent in secondary clarifiers and recycled back to the front of the aeration tanks to maintain the microbial population. Most of New York's 14 plants also perform some level of nutrient removal, the reduction of nitrogen and phosphorus from the wastewater, which has become increasingly important as regulators have recognized that excess nutrients are a significant driver of the algae blooms and oxygen depletion that characterize impaired water quality in the harbor and the surrounding waterways. Nutrient removal requires additional biological or chemical treatment steps beyond basic secondary treatment, and retrofitting existing plants to achieve it has been one of the major infrastructure investments of the past 2 decades. By the time the treated water, now called secondary effluent or treated effluent, leaves the secondary clarifiers, it is, by most visual measures, indistinguishable from moderately clean water. It is not drinking water. It should not be drunk. But it is something that can be returned to the natural environment without immediately killing everything in it, which is a considerable improvement on the situation that existed before the treatment plants were built. Before the water goes back to the river or the harbor, it is typically disinfected, killed of the biological pathogens that survive the biological treatment process. New York's plants use a combination of ultraviolet light treatment and, in some cases, chlorination followed by dechlorination to achieve the pathogen reduction required by their discharge permits. The discharge permits themselves are issued under the Federal Clean Water Act and set specific numerical limits on what the plants can put into the water, limits that have generally become more stringent over time as the science of water quality has improved and as the goals for the harbor have been raised. The clean effluent, clean being a relative term but a meaningful one, flows through outfall pipes into the rivers and the harbor, where it rejoins the natural water cycle. The outfall pipes are not always as far from shore as you might like, and the treatment is not perfect. And there are days when the system is under stress and the effluent is not as clean as it should be. But on a normal day, what the treatment plants return to the water is dramatically, genuinely, meaningfully better than what would be there without them. This is not a small thing. And the story of why the treatment plants were built, why a city that had been dumping raw sewage into its harbor for a century suddenly decided to do something different, is one that involves an amount of political drama that you might not expect from a story about sewage treatment. Chapter 6. Newtown Creek. The most important place nobody already visits. Between Brooklyn and Queens, there is a body of water that most New Yorkers have never seen and fewer have deliberately visited. It is approximately 3.5 miles long. It runs in a roughly east-west direction, with a series of tributary creeks: English Kills, Whale Creek, Maspeth Creek, branching off from its main channel. Its banks are lined with industrial facilities, fuel storage tanks, concrete plants, scrap yards, warehouses, facilities whose functions are not immediately obvious from the outside. In the middle distance, the skyline of Manhattan is visible. The water is dark. This is Newtown Creek, and it is one of the most historically significant and environmentally complicated bodies of water in New York City, which is saying something in a city that has no shortage of historically significant and environmentally complicated bodies of water. Newtown Creek has been an industrial waterway since the mid-19th century. The combination of deep water, proximity to the harbor, and distance from the residential center of Manhattan made it an ideal location for the industries that a growing city needed but didn't want to smell. Petroleum refining arrived in the 1860s, when John D. Rockefeller's Standard Oil established refineries along the creek's banks that at one point processed roughly a third of the nation's oil. Chemical manufacturers followed. Fertilizer plants, rendering facilities, a glue factory that operated for decades and whose legacy is still present in the soil. The creek also received the overflow from the combined sewer system, the portion of New York's sewer network that served the surrounding neighborhoods and discharged directly into the creek when the system was overwhelmed, which in the early 20th century was a more or less continuous condition during and after rain events. By the mid-20th century, Newtown Creek was, by most objective measures, not so much a body of water as a repository of industrial history in liquid form. The oxygen content of its water was essentially zero in its lower reaches. Fish had not been reliably observed in it for decades. The sediment in its bottom was layered with petroleum products, heavy metals, and the chemical legacy of a century of industrial activity. In 1978, a massive oil spill, later estimated at 17 to 30 million gallons, making it one of the largest oil spills in American history, was discovered in the soil and groundwater beneath the neighborhood of Greenpoint, Brooklyn. The oil had been seeping into the ground from petroleum storage and refining operations for decades and had accumulated in a plume that extended beneath entire city blocks, gradually leaching into the creek. Most people don't know about the Greenpoint oil spill. It is one of those environmental disasters that happen slowly enough, and in an industrial area inconvenient enough, that it never achieved the public attention that its scale arguably deserved. Cleanup operations, primarily by ExxonMobil and BP, the successor companies to the original Standard Oil operations, have been ongoing for decades and are not yet complete. Newtown Creek sits at the center of all this history for a reason that goes beyond industrial geography. It is the site of the largest wastewater treatment plant in New York City. The Newtown Creek Wastewater Treatment Plant, which occupies a large portion of the creek's northern bank in the Greenpoint neighborhood of Brooklyn, serves approximately 1 million residents of Brooklyn and Queens. It processes, on average, around 300 million gallons of wastewater per day. On a heavy rain day, that number can increase dramatically. It is one of the busiest wastewater treatment plants in the United States. The plant is also, by the standards of such facilities, an architectural curiosity. In 2010, it opened a visitor facility, the Newtown Creek Nature Walk, a public greenway along the creek's edge, and the digester eggs, 8 massive silver egg-shaped structures that serve as the plant's anaerobic digesters. The digester eggs are 40 feet in diameter and 140 feet tall, and they are visible from considerable distance, rising from the industrial landscape of Greenpoint like something from a science fiction film or a very large breakfast. They were designed by the architectural firm Polshek Partnership, now Ennead Architects, and they represent a self-conscious attempt to make visible, to make architecturally dignified, an infrastructure facility that is usually hidden or disguised. It's interesting that this was felt to be necessary or desirable. It suggests a recognition that the work that happens inside these facilities is significant enough to deserve acknowledgement, and that the people of the surrounding neighborhoods, who have lived near and with and somewhat at the mercy of the plant for decades, might deserve something more than a utilitarian industrial structure on their waterfront. The digester eggs are also, it should be noted, where one of the most interesting and underappreciated aspects of modern wastewater treatment happens, which is the subject we'll turn to shortly. First, though, a word about the choice of Newtown Creek as the location for the plant, because it was not inevitable and it was not without controversy. And the history of how that decision was made is the history of how infrastructure decisions are always made in cities. Imperfectly, politically, with consequences that extend far beyond the immediate engineering question. The Newtown Creek plant began operations in 1967, at the end of a period of intensive investment in New York's wastewater treatment infrastructure that was driven, in large part, by state and federal regulatory pressure. New York State had been pushing the city to clean up its harbor since the 1930s, when the first treatment plants were built, but progress had been slow and fitful, interrupted by the Depression and the Second World War, and the perpetual fiscal challenges of governing a very large and very complicated city. The Federal Clean Water Act of 1972, which established enforceable standards for water quality and created a framework of permits and penalties that gave the federal government a real leverage over municipal wastewater dischargers, was the catalyst that finally forced the remaining gaps in the system to be closed. The neighborhoods around Newtown Creek, Greenpoint, Williamsburg, Maspeth, Long Island City were industrial and working class, and, in the politics of mid-century New York, not particularly well positioned to resist the siting decisions of city agencies. This is a story that has been repeated across New York and across the country. Wastewater treatment plants, like other environmental burdens, tend to end up in communities that have less political power to resist them. The environmental justice implications of this pattern are well documented and are, in many respects, still being addressed today. The neighborhoods around Newtown Creek have changed considerably since 1967. Greenpoint and Williamsburg have gentrified significantly, and the residents who live there now are both more aware of the plant and more inclined to advocate about its effects on their neighborhood, which has produced an interesting dynamic in which a facility that was built in a community that lacked the power to object is now surrounded by a community that is very willing to engage. The plant has responded, in some ways, by becoming more of a community institution and less of an industrial imposition. The nature walk, the digester eggs, public tours, education programs. Whether that fully addresses the historical inequity of the siting is a different question. Chapter 7. The biology of what we throw away. Let's talk about the biology, because it is genuinely fascinating, and because it is one of those cases where the scientific explanation for what happens is significantly more interesting than the surface-level description would suggest. When we talk about wastewater, we tend to focus on the liquid, the billions of gallons of water that move through the system every day, carrying their cargo of organic and inorganic material. But a wastewater treatment plant produces two output streams, not one. It produces treated effluent that goes back to the water, and it produces sludge, the concentrated organic material that is removed from the water during the treatment process. The sludge is, in some ways, the more interesting product, because what happens to it is a story of biology doing what biology has always done, which is to take organic material that looks like waste and transform it into something useful. The primary sludge collected from the primary clarifiers, combined with the biological mass from the secondary treatment process, called waste-activated sludge, is thick, wet, and, to put it gently, strongly scented. In its raw form, it is not stable. The organic material in it continues to decompose, producing gases and odors, and presenting a disposal challenge that is, at scale, non-trivial. The solution to this challenge is anaerobic digestion, and this is where the digester eggs at Newtown Creek come in. Anaerobic digestion is what happens to organic material in the absence of oxygen. It is the process that creates methane in landfills. It is the process that happens at the bottom of a swamp. It is, in a biological sense, the process by which the earth recycles organic carbon, and it has been operating continuously since before multicellular life evolved. What wastewater engineers have done is put it in a tank and control it and capture its products. Inside an anaerobic digester, whether that digester is a conventional cylindrical concrete tank or one of Newtown Creek's spectacular eggs, the raw sludge is heated to approximately 95 to 100 degrees Fahrenheit, which is the temperature that maximizes the activity of the anaerobic bacterial community. The bacteria consume the organic material in the sludge in a multi-stage process, with different groups of microorganisms specializing in different stages of the breakdown. The end products of this process are two things: a stabilized, reduced volume solid called digested sludge or biosolids, and biogas. The biogas is primarily methane, typically around 60% methane and 35% carbon dioxide, with small amounts of other gases. And methane, as anyone who has a natural gas stove knows, burns. It produces energy. New York City's treatment plants capture the biogas from their digesters and use it to generate electricity on site, to heat the digesters themselves, which is why they need to be maintained at 95 degrees, and to run other plant equipment. At Newtown Creek, the 8 digesters produce enough biogas to supply a significant portion of the plant's electricity needs. Other plants similarly capture and use their biogas, reducing their reliance on grid electricity and reducing the greenhouse gas emissions that would result if the methane were simply vented to the atmosphere. This is not a small consideration. Methane is approximately 80 times more potent as a greenhouse gas than carbon dioxide over a 20-year period, and the quantity of methane that would be generated by the decomposition of New York's wastewater sludge, if it were simply left to decompose in landfills or open storage, would be environmentally significant. Capturing and burning it, producing carbon dioxide in the process, which is itself a greenhouse gas, but a much less potent one, is a meaningful net improvement. The digested sludge, the biosolids that remain after the anaerobic digestion process is complete, is a dark, relatively stable material with a soil-like consistency when dried. It has lost a significant portion of its volume compared to the raw sludge that went in. It no longer smells particularly offensive. The anaerobic digestion process stabilizes the organic material and reduces the compounds responsible for the worst odors. And it contains a significant concentration of nutrients, nitrogen and phosphorus primarily, that are genuinely valuable in agricultural contexts. What to do with the biosolids is a question that New York City, like every other large city with a wastewater treatment system, has been wrestling with for decades. The answer has changed several times over the course of the 20th century, and the current answer is still, in some respects, provisional. Until 1992, New York City dumped its sewage sludge in the ocean. This practice, which is now illegal under both federal and international law, was the subject of significant scientific concern for decades before it was finally ended. The dumping site was in the Atlantic Ocean, approximately 106 miles southeast of the entrance to New York Harbor. a location that was known, without apparent irony, as the 106-mile site. The environmental effects of decades of ocean sludge dumping at this location have been the subject of considerable scientific study, and they were not trivial, though the distance from shore meant they were less immediately visible than the effects of closer-to-shore disposal would have been. The end of ocean dumping in 1992 forced New York to find other solutions. The current approach involves a combination of land application, spreading the biosolids on agricultural land in the southeastern United States and elsewhere, where their nutrient content has genuine value, and increasingly, other beneficial uses. The biosolids are processed at the treatment plants or at dedicated solids handling facilities, dried or pelletized in some cases, and transported to their ultimate destination. It is, logistically, a considerable operation. New York City generates approximately 40% of the total biosolids produced in New York State, and managing that volume sustainably is an ongoing challenge. There are also, increasingly, emerging approaches to biosolids management that move beyond simple disposal or land application. Pyrolysis, the thermal decomposition of organic material in the absence of oxygen, can convert biosolids to a carbon-rich material called biochar, which has potential applications in soil amendment and carbon sequestration. Advanced digestion technologies can increase the energy yield from the biogas production process. Struvite recovery, the precipitation of magnesium ammonium phosphate from the digester liquor, can produce a slow-release fertilizer from the phosphorus in the biosolids. These technologies are at various stages of development and deployment, and the economics are not always favorable, but they represent the direction in which the field is moving. The point, underneath all of this detail, is that what we throw away is not nothing. It contains energy. It contains nutrients. It contains materials that have value, if you can extract them efficiently. The wastewater treatment plant is not just a facility for neutralizing a problem. It is, or can be, a resource recovery facility, taking something that looks like waste and finding in it something useful. This reframing, from waste treatment to resource recovery, is one of the more intellectually interesting shifts happening in the wastewater industry today. It doesn't resolve all the challenges, and it doesn't make the job easy or the smell go away. But it represents a different way of thinking about what the plants are for and what they can do. Chapter 8. The People Nobody Sees. Workers in the Underground. At some point in this story, it is worth pausing and talking about the people, not the engineers who designed the system, or the politicians who funded it, or the scientists who study it. The people who work in it every day, in conditions that are, to put it gently, not what most people would choose. There is a class of workers in New York City called competent persons in the regulatory terminology. Workers who have been specifically trained to work in what OSHA classifies as confined spaces, which include sewers, manholes, and other enclosed underground environments where atmospheric hazards can develop. These workers are employed by the city's Department of Environmental Protection, DEP, by contractors who maintain the sewer infrastructure, and by a range of utility and construction companies that work in and around the underground environment. The world they work in is not accessible to most people. You can look down into a manhole from the street and see the top of a ladder and a circle of light, and, if the geometry is right, the vague suggestion of a tunnel below. What you cannot see from the manhole cover is the actual scale and character of the environment below, which varies enormously depending on where in the city you are. In residential neighborhoods, the local sewers are small and tight, 4-inch, 6-inch, 12-inch pipes that a worker cannot enter and can inspect only with cameras or probes. But the larger sewers, the collector sewers, the trunk sewers, the interceptors, are a different matter. The larger interceptors in New York can be 8, 10, 12 feet in diameter. They are accessible. Workers can and do enter them. They wear full protective gear, self-contained breathing apparatus, waterproof suits, safety harnesses, communication equipment. They work in teams, with at least one person remaining above ground to monitor conditions and respond in an emergency. They carry gas monitors that continuously measure the concentration of hydrogen sulfide, methane, carbon dioxide, and oxygen in the air around them. The hydrogen sulfide issue deserves a brief explanation because it is one of the less intuitive hazards of sewer work. Hydrogen sulfide is produced by the anaerobic decomposition of organic material, which happens in any sewer that retains standing water or sewage. At low concentrations, it has the characteristic smell of rotten eggs. At higher concentrations, above about 50 parts per million, it begins to paralyze the sense of smell, so you can no longer detect it by odor alone. At concentrations above 100 parts per million, it can cause rapid loss of consciousness and death. In an enclosed space like a large sewer tunnel, pockets of high-concentration hydrogen sulfide can accumulate and are essentially invisible and, above certain concentrations, undetectable by smell. This is not a theoretical hazard. Sewer workers have been killed by hydrogen sulfide in exactly the way the textbooks describe. A worker enters an enclosed space, encounters a pocket of high-concentration gas, loses consciousness, and collapses in a space where rescue is difficult and time is short. The colleagues who attempt rescue without proper equipment are themselves at risk. Multiple fatalities have occurred in exactly this pattern in sewers across the United States and around the world. The protocols that govern confined space entry in New York's sewer system are detailed and seriously enforced, precisely because the hazards are real and the consequences of getting it wrong are irreversible. Workers are required to test the atmosphere before entry, to maintain continuous air monitoring throughout their time underground, and to have a clear rescue plan in place before anyone goes below. The safety record of modern sewer workers is significantly better than it was in earlier decades, when the hazards were less well understood and the protective equipment was less sophisticated. But the work is still demanding in ways that go beyond the atmospheric hazards. The physical environment is what it is: confined, often wet, dark, except for the lights the workers carry, and permeated by smells that most people encounter only briefly and involuntarily when passing a backed-up drain. The workers who spend their careers in this environment develop a professional relationship with it that most outsiders find difficult to fully comprehend. There is a tradition, among the people who work in and on New York's sewer system, of black humor, of finding the specific comedy in the specific absurdity of their situation. The objects that people put into the sewer system provide an essentially endless source of material. The sheer variety and occasional implausibility of what turns up in the screens and in the tunnels gives rise to stories that circulate through the workforce and that are, in context, genuinely funny in a way that they are difficult to convey without context. Beyond the sewer workers, the treatment plants employ several categories of workers who do not work underground, but whose work is equally essential and equally invisible to the public. Operators monitor and control the treatment process, adjusting equipment, taking samples, responding to upsets, the technical term for when something in the treatment process goes wrong and the effluent quality begins to decline. Laboratory technicians analyze samples from throughout the treatment process, measuring the biological oxygen demand, the suspended solids, the nutrient levels, the pathogen counts. Maintenance workers keep the mechanical equipment, the pumps, the aerators, the scrapers, the blowers, running continuously. Electricians maintain the power systems. Engineers plan and design the upgrades and expansions that keep the plants capable of meeting their permit requirements as the regulatory standards evolve. These are not glamorous jobs in the conventional sense. They don't appear on television or in movies. They are not the subject of profiles in lifestyle magazines. The people who do them are paid public sector salaries, which in New York City are reasonable but not spectacular, and they work shifts that cover 24 hours a day and 365 days a year, because the system doesn't take holidays. And the system, to be fair, is not always kind to the people who run it. Extreme weather is not a problem that wastewater operators can choose to sit out. During Hurricane Sandy in 2012, several of New York's treatment plants were flooded and temporarily shut down, discharging raw or undertreated sewage into the harbor in quantities that were, by any measure, significant. The workers who were there during the storm were there not by oversight but by choice, or rather, by the professional understanding that if they weren't there, the damage would be worse. In the aftermath, they were there again, in flooded facilities with damaged equipment, working to restore service to the millions of people who depended on the plants. This kind of thing, the willingness to be in the difficult and unglamorous place when the difficult and unglamorous place needs people, is not unique to wastewater workers. It characterizes, in various ways, the people who work in all of the invisible infrastructure systems that keep cities running. But it is particularly characteristic of the wastewater world, where the work is never more than a single system failure away from becoming very immediately and concretely important to every single person in the city. The people nobody sees are keeping the city alive. This is not an exaggeration. Chapter 9. Rainfall and the problem it creates. On a dry summer day in New York City, the sewer system carries approximately 1.1 to 1.3 billion gallons of wastewater to the treatment plants. That's the baseline. That's what the system was designed to handle, more or less, with some capacity margin built in. Then it rains. Rain in New York City does not fall gently and absorb into meadows and filter through soil layers to slowly recharge the groundwater. Rain in New York City falls on rooftops and streets and parking lots and sidewalks and essentially every impermeable surface you can imagine, because Manhattan is nearly 98% impervious cover, and the other boroughs are not far behind in their developed areas. The rain does not have anywhere to go except into the storm drains, which connect to the sewer system. And here is where that decision made in the 1850s and 1860s, the decision to build a combined sewer system rather than a separate system, comes home to roost. In a separate sewer system, the stormwater and the sewage would flow in different pipes. The stormwater could discharge directly to the nearest waterway without treatment, because stormwater, while it picks up pollutants from impervious surfaces, does not contain the same level of biological contamination as sewage. The sewage would flow to the treatment plants. the two streams would not meet. In New York's combined sewer system, which covers about 60% of the city's sewer service area, primarily the older, more densely built neighborhoods of Manhattan, Brooklyn, and the Bronx, the stormwater and the sewage share the same pipes. On a dry day, this is not a problem, because the combined flow is within the capacity of the system. But when it rains, the volume of stormwater entering the combined sewers can be enormous, and the system is not designed to carry to the treatment plants everything that all those rooftops and streets and parking lots shed during a storm. What happens when the volume of flow in a combined sewer exceeds the capacity of the interceptors to carry it to the treatment plant? The excess flow goes somewhere. In New York's system, it goes to what are called combined sewer overflow, CSO outfalls, points where the combined sewer system discharges directly to the rivers and the harbor when the system is overwhelmed. There are approximately 460 combined sewer overflow outfall locations around New York City. On a dry day, they do nothing. When it rains, specifically when the rainfall generates enough runoff to exceed the interceptor capacity, they discharge. What they discharge is a mixture of stormwater and sewage, diluted by the stormwater, certainly, but still containing pathogens, nutrients, and whatever else was in the sewers. The total volume of combined sewer overflow discharged to New York's waterways in an average year is approximately 20 to 30 billion gallons. This is not a small number. It is the primary remaining source of water quality impairment in the harbor and the surrounding waterways. And it is the reason that swimming is prohibited at most of New York's waterfront areas for periods after significant rain events. The environmental and public health implications of combined sewer overflow are real and are taken seriously by both the DEP and the state and federal regulators who oversee New York's water quality compliance. The city has invested billions of dollars in CSO abatement since the 1990s, and it has a long-term control plan required by the Federal Clean Water Act and approved by the EPA that commits it to further significant reductions. The challenge is that solving the CSO problem fully and permanently is extraordinarily difficult and expensive in a city like New York. The full separation of the combined sewer system, replacing it with separate storm and sanitary sewers throughout the 60% of the city that currently has combined sewers, would require digging up essentially every street in those areas and replacing two separate pipe systems, a project whose cost would be measured in the tens or hundreds of billions of dollars, and whose disruption would be essentially incomprehensible. This is not being proposed as a serious option. What is being done instead is a combination of approaches. Some areas of the city are being converted to separate sewers when other infrastructure work is being done in the same area, resynchronizing the investment, so to speak. New interceptor capacity is being added in areas where the existing interceptors are most frequently overwhelmed. Large underground storage tunnels, the most dramatic of which is the Staten Island Bluebelt system and a proposed deep tunnel system in other boroughs, are being designed or constructed to capture CSO during heavy storms and hold it for treatment after the storm passes. And increasingly, the city is investing in green infrastructure. Green infrastructure, in the wastewater context, means using natural processes to absorb and filter stormwater before it reaches the sewer system. Green roofs that retain rain on rooftops. Bioswales, planted channels in the roadway that slow and infiltrate runoff from streets. Permeable pavement that allows water to seep through rather than running off. Constructed wetlands, rain gardens. These approaches are less dramatic than the deep tunnel option. They don't involve the kind of massive engineering achievement that you can point to and say, "There, we built that. We solved the problem." What they do is disaggregate the solution across thousands of small interventions distributed throughout the watershed, each one reducing the stormwater that enters the sewer system by a modest amount, the aggregate of all of them together, adding up to a meaningful reduction. The Green Infrastructure Program in New York City is one of the largest urban green infrastructure programs in the United States, and it has been expanding steadily since its inception in the mid-2000s. It is also, arguably, more resilient than the tunnel approach in certain respects. Green infrastructure is distributed, so a single failure doesn't defeat the whole system. It provides co-benefits beyond stormwater management, urban cooling, improved air quality, aesthetics, neighborhood livability. And it involves the communities that live in the neighborhoods where it's installed in a way that a tunnel beneath the street does not. Whether the combination of increased interceptor capacity, new storage tunnels, and green infrastructure will be sufficient to meet New York's CSO reduction commitments is a question that engineers and regulators are still working through. The target is ambitious, the obstacles are real, and the rainfall patterns of the coming decades, as climate change increases the frequency and intensity of extreme precipitation events in the Northeast, may shift the challenge in ways that current planning cannot fully anticipate. This is one of those problems that does not have a clean solution. It has a series of partial solutions that together, if they work, will get you most of the way there. And most of the way there will, in this case, have to be enough for a while. Chapter 10: The Harbor That Was Dying and the Harbor That Came Back. In the 1970s, New York Harbor was in a condition that anyone who experienced it still remembers with a certain retrospective discomfort. The water was dark. The smell near the waterfront was not subtle. Swimming was not only prohibited, but was, in most areas, obviously unwise in a way that went beyond legal prohibition. Fish were present in the harbor, but in numbers and variety that reflected a severely degraded ecosystem. Oysters, which had once been so abundant in New York Harbor that they had been a staple food of the poor, and whose reefs had extended across significant portions of the harbor floor, filtering enormous volumes of water, were long gone. The last commercial oyster harvest in the harbor had taken place in the early 20th century. The harbor's condition in the 1970s was not an accident. It was the cumulative result of the choices that had been made, mostly by default, since European settlement. Industrial pollution, combined sewer overflow. For much of the city's history, essentially untreated sewage discharging directly into the surrounding waters. The natural resilience of the harbor had absorbed what it could for as long as it could, and by the middle of the 20th century, it had been absorbing too much for too long. The passage of the Clean Water Act in 1972, officially the Federal Water Pollution Control Act amendments of 1972, was the legislative turning point. The law established the goal that all navigable waters of the United States should be fishable and swimmable by 1983, an ambitious target that, it turned out, could not be met on that timeline, but that established a direction and a set of enforcement mechanisms that changed the trajectory of water quality across the country. For New York, the Clean Water Act meant, most importantly, that the city could no longer delay the completion of its wastewater treatment infrastructure. The remaining gaps in the system, areas of the city that were still discharging to the water without treatment, had to be addressed. The existing plants had to meet specific permit limits, and the permit limits became more stringent over time. The construction of the Newtown Creek plant in 1967, just before the Clean Water Act, and the completion of the remaining plants through the 1970s, meant that by the early 1980s, New York City was treating essentially all of its dry weather wastewater flow before discharge. The effect on the harbor was measurable, though not immediate. Dissolved oxygen levels in the harbor began to recover. The heavy algae blooms that had characterized the harbor's most impaired zones began to decrease. But the recovery that has happened in New York Harbor since the 1980s has been, by any honest accounting, one of the more remarkable environmental restoration stories in the United States. The harbor today supports species that hadn't been reliably observed there for decades. Striped bass have returned to the harbor in numbers that support a recreational fishery. Bluefish, Atlantic sturgeon, ancient, magnificent, Jurassic-looking creatures that can grow to 14 feet in length, have been documented in the harbor and in the Hudson River in increasing numbers. Dolphins have been spotted in the harbor. Seals haul out on jetties and ledges around the harbor in winter, eating the fish that have returned to water that is now clean enough to support them. The oysters have not come back on their own, but there are now active restoration projects, including the Billion Oyster Project, which is working to restore native oyster reefs to the harbor, that are transplanting juvenile oysters onto artificial reef substrate throughout the harbor and monitoring their survival. The oyster restoration is partly symbolic, a marker of the harbor's recovery, and partly functional. Oysters filter water extremely efficiently, and a significant oyster population in the harbor would provide ongoing water quality benefits. Early results have been cautiously encouraging. The harbor's recovery has also made possible something that would have seemed almost science fiction in the 1970s. People swim in New York Harbor now. Not everywhere, and not without checking the water quality conditions. Combined sewer overflow events after rain still cause temporary closures, but there are designated swimming areas at various points around the harbor and the surrounding waterways where people swim safely. The annual Ironman triathlon includes a swim in the Hudson River. The Coney Island Polar Bear Club has been plunging into the ocean at Coney Island in winter for decades, but the water quality today is categorically different from what it was 50 years ago. This recovery did not happen by itself, and it is not permanent. It is the result of ongoing investment in wastewater treatment infrastructure and ongoing operation of that infrastructure by the people who work in it every day. If the treatment plants stopped operating, or if the funding for their maintenance and operation were withdrawn, the harbor would not take long to return to a condition closer to what it was in the 1970s. The recovery is real, but it is maintained by continuous effort, which is, again, one of the things about infrastructure that is easy to overlook. It doesn't stay fixed. It requires maintenance, investment, operation, and management every single day. A piece of infrastructure that is neglected returns to a non-infrastructure condition on a timeline that is much shorter than the timeline required to build it in the first place. The harbor's story is also a reminder that the natural world, given the chance, is capable of significant recovery. The salmon have returned to rivers in New England that were once dead with pollution. Bald eagle populations have rebounded from near extinction to widespread presence. The Cuyahoga River in Ohio, which famously caught fire in 1969 due to the industrial waste floating on its surface, now supports fish populations and recreational use. These recoveries required sustained effort and meaningful sacrifice, but they happened. The natural world is not infinitely resilient, but it is considerably more resilient than the environmental despair of the 1960s and 1970s sometimes suggested. New York Harbor's recovery is part of that larger story of what is possible when you actually decide to fix something and sustain the effort to fix it. Chapter 11. Biosolids. The strange second life of sewage. There is a truck leaving the Newtown Creek wastewater treatment plant right now, or close to it. Maybe it's 3 in the morning. Maybe it's 9 at night. The plant runs continuously, and its outputs are continuous, and the trucks that carry those outputs follow a schedule that accommodates the plant's production, rather than convenient daylight hours. The truck is carrying biosolids. Biosolids, the processed, treated, stabilized organic material that remains after the treatment process removes it from the water, is the output that the wastewater industry has, historically, found most difficult to talk about in public. This is understandable. The provenance of biosolids is not something that lends itself to comfortable dinner conversation, and the word biosolids itself is an industry coinage from the 1990s, designed in part to create distance between the product and its origin in the public's mind. The distance is real, though. Digested biosolids are not the same material that entered the sewer system from households and industry. They have been subjected to anaerobic digestion, which destroys pathogens and significantly reduces the volume and mass of the material. They are classified by the EPA when they meet certain quality standards as Class A or Class B biosolids, categories that correspond to specific limits on pathogen levels and specific allowed uses. Class A biosolids, which have been treated to very low pathogen levels, can be applied to food crop land and are in some cases marketed as soil amendments or fertilizers. Class B biosolids have been treated to reduce pathogens substantially, but not to the levels required for unrestricted use, and they are applied to agricultural land under specific conditions: non-food crops, setbacks from water bodies, restrictions on public access during and after application. New York City's biosolids are managed by the DEP under contracts with private operators who receive the material from the treatment plants and arrange for its transport and ultimate use or disposal. The logistics are extensive. New York generates, depending on the season and the weather, somewhere in the range of 1,000 to 1,200 dry tons of biosolids per day, a quantity that requires a fleet of trucks, a network of contractors, and arrangements with agricultural operations, some of them quite distant from New York. The agricultural application of biosolids is actually, from a sustainability perspective, the approach that makes most sense. The nutrients in biosolids, primarily nitrogen and phosphorus, are nutrients that agricultural soils need. Synthetic fertilizers are manufactured from natural gas for nitrogen and mined rock phosphate for phosphorus, both of which are finite resources. The phosphorus situation is particularly interesting from a long-term perspective. The mineable reserves of rock phosphate that underpin global phosphorus fertilizer production are concentrated in a small number of countries and are not renewable on any human timescale. The phosphorus in biosolids, by contrast, is phosphorus that was in the food we ate, which was grown in fields where phosphorus was applied, and which has completed a circuit through the human body and the wastewater treatment system and returned to a form that can complete the circuit again by going back to agricultural land. The closed loop is not perfect. There are losses at every stage. There are contaminants, trace metals, persistent organic pollutants, and increasingly, per- and polyfluoroalkyl substances, PFAS, the so-called forever chemicals, that accumulate in biosolids and that limit the contexts in which land application is appropriate. The PFAS issue in particular has become a significant challenge for the biosolids field in recent years, as the extent and the toxicological implications of PFAS contamination in biosolids have become clearer, and as regulations around PFAS in biosolids are tightening. The forever chemicals are called that because they do not break down in the environment under normal conditions. They were used for decades in a wide variety of industrial and consumer applications: non-stick coatings, firefighting foams, stain-resistant fabrics, and they have made their way into the wastewater stream through a variety of pathways. Treatment plants cannot remove them because the treatment processes are not designed for that, and PFAS concentrations in wastewater are generally at the parts per trillion level, where conventional treatment is ineffective. The result is that biosolids from treatment plants tend to accumulate PFAS at concentrations that are higher than in the incoming wastewater, because the biosolids contain the solids to which PFAS preferentially bind. What to do about PFAS in biosolids is, as of the time of this writing, genuinely uncertain. The regulatory picture is still developing. The technical options for removal are still being researched and developed. Some states have already imposed restrictions on the land application of biosolids based on PFAS content that have effectively eliminated the practice in those states for some generators. New York is watching the situation closely and is involved in the regulatory and technical discussions. In the meantime, the trucks keep running and the biosolids keep being produced and the logistics keep churning, because the alternative, letting the sludge accumulate at the plants without a disposal path, is not an option. The sewage does not stop being produced because the disposal question is unresolved. The system requires a solution, even an imperfect one, because standing still is not possible. This is true of a lot of things in the wastewater world. The problems are real. The solutions are imperfect. The alternatives are worse. You keep working, and you keep improving, and you hope the improvements come fast enough. Chapter 12. The water supply side, where New York's water actually comes from. We have been following the water out, from the tap, through the toilet, through the sewer, to the treatment plant, to the harbor. But water, unlike most things, is fundamentally circular. The water in the harbor evaporates and becomes clouds and falls as rain on the Catskill Mountains, and flows into reservoirs and comes down through aqueducts to become, eventually, the water in the tap that started this journey. It is worth spending some time on the supply side, because the water supply system that feeds New York City is, in its own way, just as remarkable an engineering achievement as the wastewater system, and the two systems together tell a more complete story than either one alone. New York City's water supply does not come from the Hudson River, or from any body of water within the city's boundaries, or even from anywhere particularly close to the city. It comes primarily from two watersheds in the Catskill Mountains, about 100 miles north and west of the city, and from a third watershed in the Hudson River Valley. The Catskill-Delaware watershed system is the heart of the supply. It consists of a series of large reservoirs, including the Ashokan Reservoir, completed in 1915, which alone holds 122 billion gallons of water, and the Papacton Reservoir, the largest reservoir in the system, completed in 1955, connected by a network of tunnels and aqueducts that carry the water by gravity from the mountains to the city. The Delaware Aqueduct, the main tunnel of the system, is 85 miles long and runs at depths of up to 1,200 feet below the surface. It is the longest tunnel in the world, surpassing even the tunnels that carry water to other great cities. It was completed in 1945 and carries about half of New York City's water supply. The older Catskill Aqueduct, completed in 1916, carries water from the Ashokan Reservoir south through Westchester County to the city. The even older Croton system, the direct descendant of the original 1842 aqueduct, still contributes to the supply, though its contribution is a relatively small percentage of the total. The entire system, reservoirs, tunnels, aqueducts, and distribution infrastructure, is operated by the DEP with a workforce that spans a dozen counties and involves everything from reservoir management and watershed protection to water quality monitoring and engineering. The water quality of New York City's drinking water is, by the standards of large American cities, exceptional. It routinely ranks among the best tasting and best quality tap waters in the United States. And it achieves this without filtration, which is unusual and which requires a waiver from the EPA, granted to New York because the city can demonstrate that the quality of the raw water from its Catskill and Delaware systems is sufficiently high that filtration is not necessary. The filtration avoidance determination, the EPA's formal finding that New York can avoid the filtration that federal regulations would otherwise require, depends on the city maintaining the quality of the water in the watersheds that feed its reservoirs. This has led to one of the more interesting public policy programs in American environmental history, the New York City Watershed Protection Program, under which the city has spent hundreds of millions of dollars purchasing land and development rights in the Catskill watershed, working with farmers on practices that reduce nutrient and pathogen loading to the streams that feed the reservoirs, and managing land use in the watershed to protect water quality. The economics of this program are worth understanding. Filtration plants for the volume of water New York City uses would cost something in the range of $6 to $10 billion to build and hundreds of millions of dollars annually to operate. The Watershed Protection Program costs, on an ongoing basis, a fraction of that. From a purely economic perspective, it is cheaper to protect the watershed than to build the filtration plants. From an environmental perspective, it produces benefits beyond water quality, wildlife habitat, agricultural viability, rural economies, that the filtration plant approach would not. This is one of those cases where the environmentally preferable solution and the economically rational solution happen to be the same solution, which is pleasing in principle and often difficult to achieve in practice. The water distribution system within the city, the pipes and mains and valves and meters that carry the water from the aqueducts to 8.5 million taps, is a substantial infrastructure system in its own right, and it is also old in ways that create ongoing maintenance challenges. New York's distribution mains include pipe that is a century old in some parts of the city, and the main water tunnels that carry water into and through the boroughs. City Water Tunnel Number 1, completed in 1917, and City Water Tunnel Number 2, completed in 1936, have never been shut down for inspection. They cannot be shut down without leaving large portions of the city without water. They were not designed to be shut down. They were designed to run, and they have been running without interruption for 70 and 100 years, respectively. City Water Tunnel Number 3 has been under construction, in stages, since 1970. It is one of the longest and most expensive capital construction projects in New York City history. Its first stage, which runs from the Hillview Reservoir in Yonkers to Midtown Manhattan and then to Brooklyn, was completed in 1998 and activated in 2013, after decades of construction and testing. Its second stage, which will extend the tunnel through Brooklyn and Queens, is still under construction. When Tunnel Number 3 is fully operational, it will make it possible for the first time to shut down the aging Tunnel Number 1 and Tunnel Number 2 for inspection and rehabilitation, something that engineers have wanted to do for decades and have not been able to do because there was no redundancy in the system. The fact that two tunnels carrying the majority of New York City's water supply have been running continuously for 70 and 100 years, without inspection, without shutdown, is one of those facts that takes a moment to fully absorb. They might be fine. Engineers believe they are probably fine, based on the performance indicators available to them. But nobody knows for certain, because nobody has looked inside them, because there has been no way to look without stopping the water, which cannot be stopped. City Water Tunnel Number 3 will, eventually, make it possible to know. That is itself a significant achievement, separate from the water it will carry. Chapter 13. Tunnels, mains, and the pressure that never stops. There is water pressure in the pipes beneath New York streets at this moment. It has been there continuously since the mains were first pressurized, in most cases many decades ago. The pressure is maintained by the elevation difference between the reservoirs and the city, gravity, again, doing its essential work, augmented by pumping where the gravity alone is insufficient. The distribution pressure in a typical New York City water main is somewhere between 40 and 80 pounds per square inch, which is the pressure needed to push water up to the upper floors of a mid-rise building and to maintain adequate flow at all the taps in the system simultaneously. In the tallest buildings, additional booster pumps take over to push water up to the heights where gravity-fed pressure is insufficient. The water mains through which this pressure flows range in diameter from the 6-inch cast iron pipes serving residential streets, some of which are original 19th century pipe still in service, to the massive 48-inch and 60-inch mains that form the backbone of the distribution system in the most heavily served parts of the city. There are approximately 7,000 miles of water mains in New York City. 7,000 miles. If you laid them end to end, they would stretch from New York to London and part way back. The age and condition of those mains is a matter of perpetual concern for the DEP. Cast iron pipe, which makes up a significant portion of the older water main stock, has a design life that is theoretically measured in decades, but which in practice, given the conditions in the ground beneath New York City, can range from a generation to more than a century. The conditions in the ground are not kind to pipe. The soil is corrosive in places. The ground moves with the seasons and with the vibration of subway trains and heavy trucks. The pipe is under continuous pressure, and the connections between pipe sections are potential failure points. Main breaks are a feature of urban life in New York City, and they occur with a frequency that reflects the age and scale of the infrastructure, rather than any particular failure of maintenance. The DEP replaces water mains continuously. It has been doing so for decades and will continue to do so for decades more. But the sheer extent of the system means that the rate of replacement can at best keep pace with the rate of deterioration, and in some periods it has not managed to do even that. A main break in a busy Manhattan street is a minor spectacle. Water erupts from the ground, sometimes with considerable force. Traffic is disrupted. The DEP crew arrives in its distinctive vehicles and sets about the considerable task of locating the break, excavating to it, and repairing or replacing the damaged section. The repair might take hours or days, depending on the depth of the pipe and the complexity of the surrounding infrastructure. During that time, the water service to buildings in the affected area may be reduced or interrupted. What you don't see during a main break, but what is happening, is an automatic response in the distribution system. The pressure reduction caused by the break propagates through the connected pipes, and the DEP's distribution system operators, watching the network from control rooms equipped with sensors and SCADA systems, respond by adjusting valve settings and pumping rates to maintain service to as much of the surrounding area as possible. The system is designed with redundancy, multiple connections to every part of the network, so that the failure of any single main does not leave its customers entirely without water. Sometimes the redundancy is more theoretical than practical, particularly in areas where the distribution network has not been adequately maintained or upgraded to reflect changes in the surrounding urban fabric. But the general principle holds. The water distribution system is a network, and networks are inherently more resilient than linear systems because there are multiple paths between any 2 points. The pressure, as I said, never stops. It is maintained 24 hours a day, 7 days a week, because the moment the pressure drops below a critical threshold in any part of the system, there is a risk of what engineers call backflow, the reverse flow of water from buildings and fixtures back into the main, which can introduce contamination into the system. The continuous positive pressure in the distribution mains is one of the fundamental safety features of the system, and maintaining it is a non-negotiable operational requirement. There is something almost meditative about this, if you let yourself think about it. Beneath the city, at this moment, in the small hours of the morning when most of the city is asleep and the demand on the system is at its lowest, the water is still moving. The pressure is still there. The pumps are running. The sensors are monitoring. The operators are watching. 8.5 million people are asleep, and the system is quietly doing what it does, maintaining the conditions that will allow those 8.5 million people to turn on their taps in the morning and find water there, exactly as they expect, without thinking about it. That is the design, and it works. Chapter 14. The Control Rooms. Managing a system too large to fully understand. Somewhere in the city, there are rooms where people sit and watch screens. The screens display information about the wastewater collection and treatment system, flows in the interceptors, levels in the pump station wet wells, status of the treatment plant unit processes, dissolved oxygen readings in the aeration tanks, effluent quality parameters, alarm conditions, weather data, tide levels in the harbor. The control rooms for New York's wastewater system are not dramatic in the way that Hollywood imagines control rooms to be. They don't have enormous screens with dramatic graphics. They don't have people running from station to station in a state of controlled urgency. They tend to look more like the operations center of a mid-size utility company, which is essentially what they are. Rooms with workstations, multiple computer monitors, communication equipment, and operators who are simultaneously watching a lot of information and deciding which of it requires action. The operators who work in these rooms are experienced, skilled, and in the characteristic manner of their profession, calm. Calmness is a professional requirement in this context. The system they are monitoring is large and complex and under continuous stress from 1,000 directions, and the appropriate response to most of the things the system presents them with is measured, methodical, and deliberate. The inappropriate responses, panic, indecision, dramatic overreaction, can cause more problems than the original alarm. The control systems for New York's wastewater infrastructure have evolved considerably over the past several decades. The original plants, built in the 1930s and 1940s, were manually controlled. Operators walked the plant, checked gauges, manually adjusted valves and equipment, took samples, and sent them to the laboratory. As the plants were upgraded in subsequent decades, instrumentation and automation were added incrementally, and what emerged is a system that is partly automated and partly manual. A system that uses sophisticated sensors and control algorithms to manage routine operations, but that relies on human judgment for the decisions that the algorithms can't handle. The algorithms, it should be noted, are handling considerably more than they used to. The activated sludge process, which is the core of secondary treatment, is sensitive to changes in the composition and volume of the incoming wastewater. And maintaining the biological population in the aeration tanks at the right density and condition requires continuous adjustment of the oxygen supply, the sludge recycle rate, and other parameters. Modern control systems can make these adjustments automatically in real time, based on sensor readings from throughout the aeration tanks, adjustments that would have required continuous manual attention in an earlier era. But the automation has limits, and the operators know them. The incoming wastewater is not a consistent material. Its composition varies with the time of day, the season, the weather, the activities of the industries and businesses connected to the sewer system. A slug of industrial wastewater that wasn't supposed to be there, or a sudden increase in stormwater inflow during an unexpected rain event, or the failure of a piece of equipment upstream, can change the character of the influent in ways that the control algorithms were not designed to handle. This is when the human judgment of the operators becomes critical. The operators also manage the interfaces between the different pieces of the system. The collection system, the sewers and pump stations, is operated somewhat separately from the treatment plants, but the two are intimately connected, and what happens in the collection system has direct implications for what arrives at the plant. Coordination between the collection system operations and the plant operations is continuous. There are also the external interfaces, the regulatory agencies that need to be notified when there are system upsets or overflows. The downstream users of the receiving waters who need to know when water quality conditions change. The public during major events like main breaks or post-storm water quality advisories. The communications function of the control room, managing the information about what the system is doing and communicating that appropriately to the right people at the right time, is as important, in some respects, as the operational function. The SCADA systems, supervisory control and data acquisition, that underpin the modern management of New York's wastewater infrastructure have also introduced cybersecurity considerations that would have seemed exotic to the engineers of the 1970s. A wastewater system SCADA network is, like any networked system, potentially vulnerable to malicious intrusion. The consequences of a successful cyber attack on a wastewater system can range from nuisance-level operational disruption to, in principle, more serious tampering with treatment processes. The industry has become much more focused on cybersecurity in recent years, and the DEP has implemented measures to protect its control systems, though the specific details of those measures are not publicized, for obvious reasons. This is one of those areas where the infrastructure of the modern world, physical systems built over decades and centuries, designed for mechanical reliability, has been overlaid with digital control systems that introduce a new category of vulnerability. Managing that vulnerability is now a permanent part of operating the system. Chapter 15. The Failures. When the system breaks, and what happens next. Infrastructure is most visible when it fails. The water main that works perfectly for 90 years is invisible. The water main that breaks on a Tuesday morning and sends a geyser 20 feet into the air on a busy midtown street is on the local news. The treatment plant that processes 300 million gallons per day without incident goes unnoticed. The treatment plant that has a power failure during a storm and discharges undertreated sewage for 6 hours is a controversy. This is not entirely fair to the infrastructure or the people who operate it, but it is the nature of the relationship between systems that are always running and the people who depend on them. Reliability is taken for granted. Failure is news. The failures in New York's water and wastewater system come in several varieties. There are the small, routine failures. The pump station that has a mechanical failure and needs to be repaired. The sewer main that gets blocked by a grease accumulation or a root intrusion and backs up into a few basements before it's cleared. The aeration blower that trips offline at 3 in the morning and has to be restarted. These are the daily currency of operating a large infrastructure system, and they are handled by the operations and maintenance staff as a matter of course. Most of them are repaired before anyone outside the system knows they happened. There are the larger, less routine failures, the major main break that disrupts service to a significant area, the interceptor blockage that causes a wet weather overflow at an outfall, the treatment plant process upset that results in an effluent quality violation that has to be reported to the regulators. These are more significant events. They require more resources to address, and some of them have regulatory and public consequence. And then there are the catastrophic events, the ones that are remembered and studied, and that drive lasting changes in how the system is designed and operated. Hurricane Sandy, which made landfall in New Jersey on October 29, 2012, and affected New York City with storm surge flooding that exceeded anything in the modern historical record, was the most significant test of New York's water and wastewater infrastructure in living memory. The flooding affected multiple treatment plants. The Coney Island plant in Brooklyn was among the most severely affected, with its electrical systems flooded and its operations temporarily suspended. The plant was not back to full operation for days. During the period of reduced or suspended operation, raw or undertreated sewage was discharged to the surrounding waterways. The total volume of untreated or undertreated discharges across the city during and immediately after Sandy was estimated at approximately 11 billion gallons. 11 billion gallons of untreated or undertreated sewage entering the waterways is, to be clear, a very bad thing. The water quality impacts in the immediate aftermath of Sandy were severe. Beach closures, contamination of shellfish beds, impacts on fish and other aquatic life. The human health implications for the people who had any contact with the flooded waterways in the immediate post-storm period were real. And yet, in context, the response to Sandy also demonstrated the resilience of the system in certain respects. The plants that were not flooded, and several were not flooded, either because they were at higher elevations or because they had been designed with better protection, continued to operate. The operators who remained at their plants through the storm did so under genuinely difficult and dangerous conditions, working to maintain as much treatment capability as possible. The DEP mobilized resources from across the system to support the recovery at the affected plants, and the pace of recovery was faster than might have been expected. Sandy was also a forcing event for a major program of climate resilience investment in New York's water and wastewater infrastructure. The DEP's post-Sandy capital program has included significant investment in elevating electrical equipment and other vulnerable systems at the treatment plants, constructing flood barriers, improving backup power systems, and redesigning critical systems to reduce their vulnerability to storm surge. The investments are substantial, hundreds of millions of dollars across the portfolio of plants and collection system facilities, and they represent a recognition that the climate that the infrastructure was designed for is not the climate that it will operate in for the next several decades. Beyond Sandy, there are smaller failure modes that deserve mention because they illustrate something important about how complex systems fail. The sewer system in New York City is monitored, but imperfectly. There are sensors at key points, flow monitoring stations, pressure sensors, overflow monitoring devices at the CSO outfalls. But there are also very long stretches of pipe and tunnel that are monitored primarily by the absence of any indication of a problem. This is not unusual in very old, very extensive infrastructure systems. The cost of comprehensive monitoring would be prohibitive, and the technology for non-invasive monitoring of buried pipe is still developing. What this means in practice is that some problems in the sewer system are not discovered until they have progressed to a point where they are creating visible symptoms. A sewer main that is slowly deteriorating, developing cracks, allowing groundwater infiltration, losing bedding support, may not show up in any monitoring data until it fails more significantly, at which point the failure is more difficult and expensive to address than it would have been if caught earlier. The DEP conducts regular inspection of the sewer system using CCTV cameras deployed on remote-controlled vehicles that travel through the sewers, recording the condition of the pipe walls and joints. This is methodical work done by workers who spend their days watching video footage of the inside of sewers, identifying defects, and scoring their severity according to standardized condition rating systems. The inspection data feeds into a prioritization system that guides the maintenance and repair program. But there are a lot of sewers, and inspecting all of them with sufficient frequency is a resource challenge that no city has fully resolved. The reality is that the inspection program covers the most critical and most vulnerable pipes most frequently, and works through the rest as resources permit. Between inspection cycles, things can go wrong in ways that won't be discovered until the next camera goes through. This is not negligence. It is the reality of managing infrastructure at scale, with finite resources under the pressure of all the other demands on the city's capital and operating budget. It is, however, something that keeps infrastructure managers up at night in the moments when they allow themselves to think about it. Chapter 16. The Future Beneath the Streets. There are conversations happening right now, in engineering offices, in regulatory agencies, in city planning departments, in academic research institutions, about the future of New York's water and wastewater infrastructure. These conversations involve some of the most complex engineering, financial, and policy questions that a city can face, and they are happening without the awareness of the overwhelming majority of the people whose lives they will affect. This is normal. Infrastructure planning is not a spectator sport. The decisions are technical. The timelines are long. the costs are enormous, and the immediate return on investment is often invisible in the way that all working infrastructure is invisible. It is difficult to get people excited about spending $20 billion on something they will never see and won't know is there unless it breaks. But the decisions being made now about what to build, what to repair, what to replace, what technologies to adopt, what regulatory standards to pursue, will shape the physical infrastructure that serves New York City for the next 50 to 100 years. The pipes that will be laid in the next decade will still be in the ground in 2075. The treatment plants that are being designed now will be operating in 2060. The choices being made by today's engineers, with today's knowledge and today's budget constraints, are the choices that will constrain or enable the choices of the engineers who haven't been born yet. Several major themes are shaping the future of New York's water and wastewater infrastructure. The first is climate adaptation. The consequences of climate change for urban water infrastructure are significant and multidimensional. More intense precipitation events mean more stormwater entering the combined sewers, more frequent and more severe combined sewer overflow events, more strain on the collection system. Sea level rise means that the treatment plants and pump stations near the waterfront are increasingly vulnerable to flooding from storm surge, and that the hydraulic conditions for the outfall pipes are changing in ways that may affect plant performance. Higher temperatures may affect the biology of the treatment process. The microbial communities in the activated sludge system are temperature sensitive, and warmer conditions can shift the microbial ecology in ways that affect treatment performance. The DEP has developed a climate adaptation plan for its water and wastewater infrastructure, which identifies the vulnerabilities and the planned mitigation measures for each facility and system. The plan is a living document, updated as the science of climate projections improves, and as the costs and feasibility of different adaptation measures become clearer. The second theme is nutrient management. The harbor and its surrounding waterways have water quality standards for nitrogen and phosphorus that are becoming increasingly stringent as the understanding of how nutrients drive water quality impairment improves, and as the political will to address the problem consolidates. Meeting increasingly stringent nutrient standards at the treatment plants requires either adding or enhancing biological nutrient removal capabilities, which involves significant capital investment and changes to the treatment process. New York has been investing in nitrogen removal at its treatment plants for years, and the results in the harbor are measurable. But the goals keep advancing, and the gap between where the plants are and where the standards are going is a permanent feature of the regulatory landscape. The third theme is resilience and redundancy. Sandy demonstrated, in concrete and very expensive terms, the vulnerability of critical infrastructure to extreme weather events. The response has been a sustained investment in hardening the most vulnerable facilities and improving the redundancy of the most critical systems. But resilience has a cost, and the cost of making the entire water and wastewater system fully resilient to the kinds of extreme events that climate change suggests will become more frequent is a number that is difficult to absorb in the context of a city that has many other urgent demands on its capital budget. The fourth theme is technology. The wastewater industry is in a period of meaningful technological change. Advanced treatment technologies, membrane bioreactors, advanced oxidation, ozone treatment, can achieve treatment levels that are not possible with conventional activated sludge, and they are increasingly cost competitive as the manufacturing scale improves. Digital technologies, advanced sensing, machine learning, artificial intelligence applied to process optimization are beginning to enable more sophisticated management of treatment processes. Resource recovery, capturing energy, nutrients, and other value from the waste stream, is moving from pilot scale to full-scale implementation at some facilities. New York is engaged with all of these developments, though the pace of technology adoption in a system as large and as operationally conservative as New York's water and wastewater infrastructure tends to be measured. The conservatism is not irrational. A treatment plant that is trying a new technology is also a treatment plant that might fail to meet its discharge permit, and the consequences of permit violations are real and immediate. New technology tends to be piloted at smaller, less critical facilities before being adopted at the flagship plants. The fifth theme, and in some ways the most fundamental, is finance. The capital investment required to maintain, upgrade, and adapt New York's water and wastewater infrastructure over the next several decades is measured in the tens of billions of dollars. New York's water and sewer rates, the fees paid by residential and commercial customers for water service and sewer service, are the primary source of funding for this investment, supplemented by state and federal grants and loans when available. The rates have been rising faster than inflation for decades, and the trajectory has not been comfortable for low-income households in particular. The tension between the genuine need for infrastructure investment and the genuine difficulty of paying for it, without creating hardship for the people who can least afford it, is one of the most persistent challenges in urban infrastructure finance. It does not have an obvious solution. The infrastructure needs to be funded. The people who use it need to be able to afford it. These two requirements are not always compatible at the rates that infrastructure investment requires. Various approaches have been proposed and tried. Tiered rates that charge more for higher usage and less for essential household use. Means-tested assistance programs for low-income ratepayers. Federal infrastructure funding that reduces the burden on local rates. Innovative financing structures that extend the repayment period for long-lived assets. None of these is a complete solution, and all of them involve trade-offs. The infrastructure does not wait for the financing question to be resolved. It ages. It deteriorates. The cost of deferred maintenance is, almost always, greater than the cost of timely maintenance, a lesson that has been learned expensively many times. The incentive to defer is always present, because the consequences are in the future and the savings are in the present. The consequence is that infrastructure is almost perpetually in a condition that is somewhat behind where it ideally should be. This is not unique to New York. It is the condition of water and wastewater infrastructure across the United States and in most of the developed world. The scale of the deferred maintenance backlog in American water infrastructure is, by the estimates of the professional organizations that track it, in the trillions of dollars nationally. The Infrastructure Investment and Jobs Act of 2021 provided significant new federal funding for water infrastructure, the most significant new federal investment in the sector in decades. But it addresses a fraction of the total need. The gap between what is needed and what is funded is a fact that the people who work in the system live with every day. They make choices, prioritize within finite budgets, extend the life of equipment past its nominal design life through careful maintenance, defer the less urgent in favor of the more urgent, and manage the system as well as it can be managed given the resources available. This is, in a way, a very human story. Not a story of triumph or of failure, but of the perpetual, imperfect, necessary effort to manage something that is too large and too complex to be fully mastered and too important to be allowed to fail. Epilogue. The quiet agreement. It is late now or early. That ambiguous hour when the city is as close to quiet as it ever gets, and the streets are mostly empty, and the few people who are out are moving through a city that seems, at this hour, both familiar and strange. You have probably flushed a toilet in the last several hours, or you will in the next several, without thinking about it. This is appropriate. The system was designed to be invisible, to require no thought from the people who use it, to work in the background of daily life, with a reliability so complete that its absence is essentially unimaginable. Unimaginable except, perhaps, on the evidence of history, which tells us what life was like before the system existed. The cholera epidemics of the 19th century, the collect pond, the harbor thick with the effluent of a city that had not yet invented the means to manage its own waste, the 5 Points neighborhood built on saturated ground, the great stink. Those things were not so long ago. 150 years sounds like ancient history, but it is within the living memory of the great-grandparents of people alive today. The system that was built between then and now. The system of pipes and tunnels and pumps and treatment plants and reservoirs and aqueducts and control rooms and the people who staff them was built in that time, mostly within the lifetimes of the last 3 or 4 generations. It was built by people who had names and who ate lunch and who went home at the end of their shifts.